In this video I will solve the problem of a classical crystal or an infinite chain of classical oscillators, and I will determine the normal modes in this system. And as I mentioned, I will do it actually in the chain, which means it's in 1D. And I should mention that actually I could have done it in 2 dimensions or 3 dimensions. It would have been a little bit more complicated, but otherwise actually the difference, the key features of the solution are pretty much the same in 1 dimension and higher dimensions, apart from some polarization effects. For this reason I will just concentrate on the simpler case of 1D, but we could have done it in any dimension. So the specific model I'm going to consider is presented here. So we'll consider a one-dimensional chain. So we should imagine that this is an infinite chain. Actually, more specifically, I will consider so-called periodic boundary conditions for simplicity, but in an infinite system it doesn't really matter. And so in this chain, as you can see, I have 2 types of atoms. Well, these guys, the brown and red circles, they correspond, well, in my model, to an atom of such 1D crystal. And the positions of atoms will be labeled by x sub n for lighter atoms and capital Y sub n for heavier atoms. And the index n here corresponds to, in some sense, to an elementary cell. So here this elementary cell would be one lighter atom and one heavier atom, and let's say the size of this elementary cell will be 2 times the distance between the atoms. And so n can be 1, 2, 3, 4, so I have an infinite series of these elementary cells. And also, for the sake of simplicity, I will be measuring the distances in the beginning of my solution in the units of this elementary cell size. So I will essentially set 2a equals to 1. So a is basically the equilibrium length of spring, and so 2a is essentially represents the symmetry of my discrete symmetry in my problem. So if I translate everything by 2a, I get my crystal. And what I'm saying here is that I'm going to be using the units where 2a is set to 1. But basically this is my problem, and so let me write down first the energy of this system. And so the energy actually is very simple to write down. So the energy, as usual, will contain the kinetic energy part and the potential energy part. And so the kinetic energy part includes the kinetic energy of all light atoms. So this letter case P sub n over squared over 2m. And the kinetic energy of the heavy atoms, so which I actually have a color code here. The sort of brownish font correspond to terms that are associated with the lighter atoms, and the red fonts naturally corresponds to terms which are associated with the heavier atoms. And then there will be a potential energy, which is just the usual Hooke's law, if you want. But I now have a Hooke's law for every single spring in this oscillator chain. So for example, in this nth elementary cell, I'm going to have a term here associated with the spring between this lighter atom and this heavier atom. And so this term essentially corresponds to this spring. But also there will be an interaction, let's say, of this heavier atom with the lighter atom from the next elementary cell, the nth plus 1 elementary cell. And so there is a term also here in this Hamiltonian, this classical Hamiltonian, associated with this nearest neighbor interaction. Now, and of course I have to sum over all these n's, and this will give me the total energy of my classical crystal. Now the next step is to solve this problem, is to write down the equations of motion for all the particles involved, and there's an infinite number of such particles. And in our case, these equations of motion are nothing but Newton's equations, well, associated with each of these particles. And as usual, well, the Newton equation is m times a, mass times acceleration, is equal to the sum of all the forces. And the force can be found as a derivative or gradient, in this case it's just one-dimensional gradient, of the corresponding potential energy with respect to the coordinate of a particle we're investigating. And so, for instance, for the lighter atoms, for the nth lighter atom, this will be the Newton law, and for the nth heavy atom, this will be the Newton law. And so if we just formally differentiate our potential energy, we get these equations of motion for the lighter atoms and the heavy atoms. And it's very natural that there are two terms in each of these equations, because this essentially corresponds to having two springs attached to each of the atoms. So for example, here, this equation, we can understand the first term as being associated with the force exerted on this heavy atom by this spring, and the second term is going to be the force exerted on the same atom by this other spring to the right. So, and the goal now is to solve these equations. Of course, it's an infinite chain of equations because n goes from minus infinity to plus infinity. So this is an integer index which labels our pairs of heavy and light atoms. So here I'm showing the same Newton's law that we derived in the previous slide, but now just slightly rewritten. So I just grouped together this 2x sub n and 2y sub n. So of course, it's a very complicated looking system of equations. We actually have an infinite system of coupled differential equations. And well, naively we could just say that it's hopeless. There's no way we can solve such a complicated model. But it turns out that using a combination of a powerful mathematical method, which we already used actually, the Fourier transform, and a reasonable physical guess, we can solve the problem in a few relatively straightforward steps. So and the method involves essentially a Fourier transform where we represent our time-dependent coordinates of the light and heavy atoms as a linear combination or an integral over a wave vector of a wave-like excitation. So here I have essentially a plane wave in one dimension. And so remember that I introduced these units of 2a equals to 1. Therefore, this wave vector multiplies just an integer label n, which labels my coordinates of my light atoms. And I represent the heavy atoms as a linear combination of their own wave with some new amplitudes, capital Y sub q. And here I use q times n plus 1/2 because this guy is shifted by 1/2 in my units of length relative to the light atom. And importantly here I have the time dependence again which is consistent with the wave-like behavior. So we assume essentially that whatever solutions there are, this solution represent waves running through this crystal. And now the next step in the solution is to plug in these trial functions into the Newton equations and to see if we can find a self-consistent solution which is consistent both with the Newton equations and with this representation. And going a bit ahead of myself, I would say that, of course, the reason I'm presenting this solution is because we will indeed find that it's self-consistent. But the self-consistency will include in a very essential way a relation between omega and q, between the frequency of the wave and the wave vector. So, this is going to be the dispersion of the waves, the possible dispersion of the waves. And basically to solve the problem in this context means to find this dispersion, basically to find omega as a function of q. So now let me consider every single term, let's say in the first Newton equation corresponding to the light atoms. So the first term on the left hand side, the second derivative of the coordinate with respect to time, the acceleration, here is going to involve the integral over all wave vectors. And I will just label this integral as integral sub q, not to write the differentials. And here I'm going to have x sub q, and the derivative of this exponential with respect to time is going to produce minus I omega squared, exponential of I qn minus I omega t. So this is just minus omega squared. Now I also have here this term of y sub n plus y n plus 1, which essentially corresponds here in this picture to having this red atom to the left and the red atom to the right. And so if I now calculate this term, y sub n plus y n minus 1, I simply can write this expression. So I have an integral sub q, capital Y sub q, and here I have a sum of two terms, e to the power I q n plus 1/2 plus e to the power I q n minus 1/2, because now this corresponds to n minus 1, e to the power minus I omega t. Or I can factor out this e to the power I q n, and here I will have e to the power I q over 2 plus e to the power minus I q over 2. And this is equal to the cosine, proportional to the cosine. So I can write it identically as an integral over q, y sub q, twice cosine of q over 2, multiplying the same exponential as in this term here. And if I put everything together, so what I'm going to get is, and basically if I focus only on the coefficients which multiply the same plane waves in each of these integrals, I can write essentially the same Newton law, but now in the Fourier space, as minus m omega squared x sub q from this guy is equal to k twice y sub q cosine q over 2, this term that we just derived, minus 2 x sub q. And this is essentially the Newton law corresponding to the light atoms written in the Fourier space. Of course, we can repeat the same kind of procedure for the second Newton law for the heavy atoms, and if we do so, we are going to get the following system of equations. So the first one we just derived, and the second one I didn't explicitly derive, but it's derived in a very similar fashion. So, well, the good thing about these equations, first of all, that instead of an infinite chain of coupled equations, I actually just have two coupled equations. Okay, you see that, of course, I have all different q's involved, so I can change my q, but there is no coupling between different q's, unlike in real space where we did have coupling between neighboring sides n. And another thing which is good is that it's no longer a differential equation. Instead of the derivative, I now have just omega squared here. So it's much easier now to deal with this essentially linear 2x2 system of equations. And to solve the remaining part, let me just rewrite the same equation in a slightly different form. I will write it as a matrix. Well, it's the same equation I just had before, but now I wrote it in a slightly different way. I wrote it as a matrix, 2x2 matrix, acting on a vector, if you want, which contains the Fourier component of the coordinate of the light atoms and the Fourier component of the coordinates of the heavy atoms. And the right hand side is 0, because if we go back, we see that all the terms here are proportional to one or the other coordinate. There is no free terms here, which is just constants. So I can write it like that, and it's equal to 0. And maybe most of you or some of you know from linear algebra that in order for me to be able to have a non-trivial solution to this equation, which is not identically equal to 0, basically a solution where x and q are not identically equal to 0, I have to ensure that the determinant of this matrix, so the determinant of this matrix vanishes. And this is the determinant of a 2x2 matrix, which I can calculate. And well, if you do so, you will get the following equation, which is the algebraic equation, and essentially it reduces to a quadratic equation. Well, formally it's an equation of the fourth order, but there is only omega squared involved, so all in all it's just a quadratic equation that I hope most of you know how to deal with. And well, what is this equation for? Okay, this is again an equation for the frequency, or more precisely for the dependence of the frequency on the wave vector, which is known as a dispersion relation. So, well, we have seen actually many dispersion relations already in this course in the context of quantum physics and also classical physics. For instance, when we talk about the energy of a particle, of a free particle, being proportional to p squared. So this is essentially dispersion relation, let's say, of an electron or any other free particle. When we talk about the dispersion relation of a photon, where omega scales linearly with the wave vector, this is, well, the dispersion relation of electromagnetic waves. So now we have here an equation which determines the dispersion relation of elastic waves, otherwise known as phonons, which can exist in this sort of simple model of a one-dimensional crystal. So now, before solving this equation, let me go back to the sort of physical, original physical units where the dimension of length is restored. So here we have this q, the wave vector, which is measured in 1/, distance. And remember that my sort of convention was that 2a, a being basically the size of the length of a spring, was equal to 1. So if we want to restore the right physical dimension, I should multiply this q here by 2a. And also, of course, 1 minus cosine squared is equal to sine squared. So I can just rewrite in the usual physical units. I can write this term as sine squared q times a. And now, well, again, this is just the quadratic equation, omega, for omega. So if I solve it, I will get two branches with a plus and minus sign. And, well, I get actually a rather nonlinear and non-trivial relation between omega and q. There are two relations, as a matter, two types of excitation, so two types of waves or normal moves that I get out of this solution. So and if I plot these dispersion relations, so this would be my omega of q, and q here is defined, I should have mentioned it before, between minus pi over a up to pi over a. So we'll get two terms. There will be a branch corresponding to a plus sign, the plus branch, which will look like this, and there will be a branch corresponding to a minus sign, which will look approximately as so. So this is omega minus, and this is omega plus. And the omega minus is called acoustic phonons, and the omega plus is called optical phonons. So as you can see, there is a gap separating these optical phonons from zero energy. So if we hit our oscillator chain with a hammer, and it's going to be a non-linear perturbation, we're going to excite all kinds of modes. But if we just touch it very slightly, very gently, and apply just a weak perturbation, there is no way we can excite an optical phonon. We're only going to excite these energy excitations in the vicinity of zero energy. So this is basically the energy, associated energy, that we need to spend in order to excite, in this case, acoustic modes. And the dispersion of these acoustic modes as q goes to 0, we'll also discuss it in the next slide, is actually linear dispersion. And this type of linear dispersion is called sound, okay? A sound-like dispersion. And the coefficient of proportionality, basically omega as a function of q in the q to 0 limit for these acoustic phonons, this coefficient of proportionality is the speed of sound. I actually forgot to mention a couple of things here. So in this equation there appears this variable mu. So mu here is simply the reduced mass, which we actually have seen before quite a few times, which is in this case the product of the mass of light atoms and heavy atoms and divided by their sum. And the last thing I'm going to mention on this slide is something about the optical phonons, namely that the existence of this optical branch is related to the fact that we have two types of atoms present in our crystal. So if we had just one type of atom, let's say these blue atoms were the only type of atoms, then we would not have had the optical branch, and we only would have had the acoustic branch. Which, by the way, the acoustic branch corresponds to what I was discussing in the end of the previous lecture, to the presence of this sort of broken symmetry in the crystal. So finally, let me calculate the speed of sound, that is the coefficient of proportionality in this dispersion of the acoustic wave as q goes to 0. So as we can see here, so if we just focus on the minus sign in this equation, okay, so if we consider the limit of q very small, then this guy can be expanded in Taylor series just up to first order, so we're just going to have qa squared instead of the sign. And also, well, this whole thing, the square root of 1 minus this 4 mu squared over m, capital M, qa squared, in the limit of small q, it can be written, again, using the Taylor series. So we have 1 minus epsilon, and epsilon is small. We can approximately write it as 1 minus epsilon over 2. So in this case, epsilon is this whole thing, and it's indeed small because we're near the zero momentum and zero energy. So we can write it approximately as 1 minus 2 mu squared mm qa squared. So if we plug it back in here, so we're going to see that 1 minus 1 gives us 0, and we have just this guy appearing. So the spectrum of the acoustic phonons in the q to 0 limit is approximately equal to k over mu 2 mu squared m qa squared. Or we can cancel these guys, and we're going to have, simply recalling the definition of the reduced mass, 2 times the stiffness divided by the sum of 2 masses, qa squared. Or if we take finally the square root of this expression, we're going to get omega minus in the q to 0 limit is approximately equal to the square root of 2k a squared m plus m times q. And this is our speed of sound. So in the next video, I'm going to redo the problem, actually in the quantum limit. And surprisingly, we're going to see that the solution is not more complicated than the classical limit. Well, I actually find that the quantum solution actually easier than the classical solution. But in any case, however you classify the solution easier or more complicated, the solution is actually going to be quite similar to what we found here. And the spectrum of the quantum phonons will turn out to be exactly equal to the spectrum of the classical phonons. So, which is another sort of striking manifestation of quantum to classical correspondence, and actually a rather complicated system. In this case, this system models a crystal.